In this lecture, we cover the dual property, which is observability and reconstructibility, the dual property of controllability and reachability, observability and reconstructibility. Let us move into it. Just look at the definitions, what we are wishing here. So we would say that a system is completely observable if for all times t1, this symbol is for all. For all t1 there exists t0 such that your t0 is between minus infinity, so from very long past till this time t1, such that by observing, st means such that by observing the output yt1, so you would have to only observe the output yt1, the initial state xt0 can be uniquely determined. So, and you want to do this for all times t1. So you are running the system, you are observing the output. You wish that I had started from t0 and right now I am at a time t1. By observing the output at this time t1, I would be able to predict from which initial condition I have started. And if and this I will be able to do if I observe the output at any time t1. At any time t1 I can observe the output. So this is how my system is evolving. I can observe the output at any of these times t1. At any point in this trajectory I can observe the output, and I will be able to infer what is my initial starting condition. Okay, initial condition, that I will be able to infer. If I am able to do that, I would say that the system is completely observable. When the initial state cannot be determined like this, then the system is unobservable. Reconstructibility. A system is completely reconstructible if for all t0 there exists t1 and t0 is less than t1, such that by observing the output yt0, the state xt1 can be uniquely determined. Here what we are trying to say is that there is a t1 now fixed at a particular position, at a particular instant. I want to estimate, or I want to understand what my state xt1 is by looking at the output yt0, the past output yt0, and your t0 can be any t0 less than t1. So you have all these t0 which are less than this particular time instant t1. You observe the output, the past output, and if you are able to reconstruct or construct this state xt1 from the past outputs, then you would say that the system is completely reconstructible. So this is the definition of reconstructibility. So here also it is almost the opposite. So in observability, you wish to understand what is the initial state by looking by noting the present state at some t1, present output. You are noting the output yt1 and you are trying to infer about the initial state xt0. In reconstructibility, you are looking at past output and trying to infer about the present state. Okay. And if a system is observable, then it is also constructible or reconstructible. So constructibility and reconstructibility are the same thing basically. If a system is observable, that means if you are able to do this thing, if you are able to infer about the past state from the present output, then the system is observable, and that will imply that it is also constructible. However, the relationship is not always true the other way around. So this is what is told in this particular slide. So observability is the ability to determine past states using present output, whereas reconstructibility refers to the ability to determine present states using past outputs. Now what is that we would be generally interested about? We would be generally interested about the reconstructibility property, which is the ability to determine present state using past outputs. Why so? See, we have made a state space representation good enough, well enough. However, always these states are not the physical quantities which are evolving in the system. Like suppose an electrical system is there, so physical quantities in the system would be your current, your voltage, all these things, but you may be constructing a state space representation using these physical quantities, but then maybe you have transformed this system and you got another state space representation. There, what these state variables are representing in the system you might not know. Okay, and this sort of thing will happen a lot of times. Even you can start with some very abstract or state variable defined for the system, which does not have any direct relationship with the physical quantities of the system. Sometimes it would happen that even if your state variables are the physical quantities of the system or some combinations thereof, many times or almost all times it will happen that you are not able to measure all the state variables. That means all the physical quantities. You are not able to measure all the physical quantities in the system. There are so many physical quantities in a complex system. Will you put a sensor to measure every other physical variable, every other physical quantity? Maybe there are also not sensors available for many of such physical quantities. So it becomes very important to basically construct the state variables from the observed output only. Now output by definition are the physical quantities which you are able to measure. Output by definition are the physical quantities which you are able to measure from the system. That is the output of the system. So you would have to basically reconstruct the states of the system using the output information available to you. So right now I would like to know what my state is, what the state of the system is. I have a set of outputs, past outputs, which I have already measured. So with the help of that I would like to reconstruct the present state. So that is what I am mostly interested in. So I am interested in the reconstructibility property of the systems. Okay. So for continuous LTI system, observability, reconstructibility imply each other. For discrete time systems, they would imply each other when the state matrix G is non-singular. To understand this property of reconstructive, whether the system is reconstructible or not, you would have to determine it, right? So you cannot sit and do experiments for obvious reasons. You have to have a mathematical procedure or a mathematical technique through which you would be able to ascertain definitely whether your system would be reconstructible or not. So for reconstructibility, we are interested in reconstructibility, but we are analyzing observability. We are analyzing observability, and in this case, the matrix that we would form is called the observability matrix. So there is no confusion here. So we are analyzing observability. We are calling the matrix also observability matrix. However, the feature or the property we are interested in is reconstructibility. That you should keep in mind. So for analyze, so what we are doing, we are writing down the output equation of the unforced system. Sorry, what happened here? Got zoomed suddenly. Yeah, it's fine. Okay, so we are analyzing the output of the unforced system, unforced LTI system without loss of generality. Why only the unforced system? What about the control input? Why we are not analyzing it? Because the control input is known to us. Whatever we are supplying to the system, that is known to us. So that part which is in the integral, so there the state equation has an expression with this part and the another integral part. That part with the integral is always known to me. So I can always subtract that part from both the LHS and RHS, right? And hence I can work with only this equation, which is the output of the unforced system. Only in this equation I am having the initial condition which I am trying to ascertain by looking at the future output. So I am trying to ascertain whether my system is observable or not. So when I am trying to do that, now I expand the exponential like before. Expanding the exponential, this is what I am getting. Please note there is an x0 sitting at the end of the bracket. Okay, so this is the entire thing, an infinite number of terms and an x0 there. Now I urge you to consider this equation OX0, where O is the observability matrix. So it is not called observability matrix yet. So suppose this is just a matrix like this. We construct a matrix C, CA, CA square, CA to the power of n minus 1 transpose. So that means this is a matrix like this: C, CA, CA square, CA n minus 1. C is a row vector, right? So CA is also a row vector. So these are so many rows, n number of rows. Suppose that this matrix that I have constructed just now is not full rank. When it is not full rank, what does this mean? If it is not full rank, it means that it has a non-trivial null space. These ideas are clear to you right now, I believe. So if this is a matrix which is not having full rank, the null space is non-trivial. That means from this equation I will get a x0 not equals to 0, which will satisfy this equation. Of course x0 equals to 0 satisfies, but I will also get an x0 not equals to 0 which satisfies this equation. At least one I will get. This will mean, since OX0 has to be 0, that means all the when we multiply OX0, all the columns must be 0, and O being this, so these are the rows. So all the rows must also be 0 because it's a 0 matrix. So CX0 CAX0, CAN minus 1 x0, all these must be 0. All these must be 0. Right? Now, by Cayley-Hamilton theorem, CALX0 will also be 0 for all L greater than equals to N, because AL can be expressed in terms of all the lower order powers of A. Okay, for L greater than equals to N, for L greater than equals to N, we can express like that. So since all these lower orders are 0, this and all higher orders from L greater than equals to N will also be 0. That means this entire thing within the bracket will become 0. This immediately leads us to the conclusion that there exists a non-zero x0. So, see, note that x0 was not equals to 0. There exists a non-zero x0, non-zero initial condition for which the output has become 0. Now you are measuring some output which is 0. Will you be able to conclude what is the initial condition when it is just that it is just something not equals to 0? You cannot conclude what that initial condition is. It can be anything. It is simply a non-zero initial condition. So that such x0 cannot be observed by the output yt uniquely. It cannot be uniquely observed. Only unique state that can be observed in this particular situation is x0 equals to 0. I can definitely say that if x0 is 0, then I can say that output 0 means the initial condition is also 0. Then it would be a unique observation. Otherwise, I will not be able to do any unique observation of the initial condition. And for this unique observation to happen, that means x0 0 must happen. X0 0 must happen. That means the matrix O that we have constructed must be full rank. Must be full rank. So this matrix must be full rank. And this matrix is called the observability matrix. That should be full rank. So again, the checking of the condition is very easy. You construct the observability matrix and then you check whether the columns are independent or not by doing the column operation. That's all. Now some other things, since we already have an understanding now of controllability matrix and observability matrix, there is a very useful feature of these two matrices with which we can find out a similarity transformation between two representations, given that they can be linked with a similarity transformation. Okay, so when you know that there are two representations given to you, you want to link them by a similarity transformation, then how to do that? How to find out that similarity transformation? So suppose that the similarity transformation P exists. So this is a precondition. We have to know that it exists. Then you can create a new system A bar B bar like this. And then for this system A bar B bar, the controllability matrix would be some C bar, which is like this: B bar, A bar, B bar, like this. Okay. Now you replace these B bar and A bars with these formulas P inverse AP and P inverse B, and then you would find that you can these things will cancel in between. These things will cancel in between. What you would find that P inverse will come out at the before this matrix B, A, B, etc., etc. So this matrix is the C matrix. That means your C bar will be P inverse C, or P would be C bar inverse. P would be C bar inverse. Okay. Similarly, it can be shown, so you can try this out. I will urge you to try this out to show that P would be O bar O inverse. You can remember these formulas, it is very easy to derive also. P is C bar inverse, and it is also equals to O bar O inverse. This will also lead to a conclusion that CO equals to C bar O bar. To note that you need invertible controllability matrices and observability matrices. This means that your system must be controllable and observable, both the systems. Okay, only then you can link the similarity transformation with the help of controllability matrices and observability matrices. Otherwise you cannot. There is a principle of duality. What are dual systems? We need to understand first. Dual systems are very plainly, like very casually we can define them. So if we have a system A, B, C, then the system A transpose C transpose B transpose is the dual of this system, and they are dual of each other actually. ABC, so if you are given a system ABC, then A transpose C transpose B transpose is the dual system. That means in the second system, this is your state matrix A transpose, this is your input matrix, the output matrix of this, you take the transpose, it becomes the input matrix. BT is the output matrix, the input matrix of the other system, you take the transpose, it becomes the output matrix. So suppose a very easy example just to highlight what we are trying to say. 1 2 minus 1 3, and maybe B is your 1 minus 1, and C is 1 0. Then the dual system would be this transpose, so this, then your this matrix would be 1 0, and this matrix would be 1 minus 1. Okay, so this is the A transpose, this is B, this is C transpose, and this is B transpose. A1 B1 C1 A2 B2 C2. What is the principle of duality? Principle of duality states that the system S1 is completely state controllable or observable if and only if S2 is completely observable or state controllable. That means S1 is completely state controllable if and only if S2 is completely observable, and S1 is completely observable if and only if S2 is completely state controllable. Why this happens? You can just check the controllability matrix and the observability matrix of system 1 and system 2, and this is what I have written down. You can very well understand by looking at these two systems, and now you can ascertain that this is basically same as this and this is basically same as this. So the controllability of system 1 infers the observability of system 2, and the observability of system 1 infers the controllability of system 2. I think I had done a mistake here in the slide, or not. Yeah, I have done a mistake actually. This should be here and this should be here. So this entry should be in this cell and this entry should be in this cell. So that is the observability matrix. This is the observability matrix of system 1 basically. So pardon me for my mistake here. So this is the observability matrix of the system 1. This is the controllability matrix of system 2 basically. So I have confused with the basically the row and the columns actually. So I hope you can understand now. Okay. So with that, I come to the end of the lecture, and hopefully this is clear to you, and thank you for your attention.